Now, yesterday, we started this example, but we didn't go through it. I mentioned the answer was 3 over 196 pi. A spherical balloon, we were talking about related rates. And the related rates questions discuss a situation which is changing as time is changing. And then they ask what's happening at an instant during, in this case, the inflation. A spherical balloon is being inflated at 3 cubic feet per second. How fast is the volume of the balloon changing when the diameter is 14 inches? So the balloon is inflating, and this question is saying, what's the volume doing at a given instant? So we need here the volume of a balloon. The volume of a sphere, which is 4/3 pi r cubed. Now, in general, you won't need to know these formulas unless we cover them. So right here, we're covering volume of a sphere, so that could show up. I'll mention a little about a cylinder later because I did post that document. But if we haven't covered a volume or a surface area formula or something like that, and I asked a question about it, I always give you the formula. More on that when we discuss the cylinder. But what is this question saying? How fast is the volume of the balloon changing? So we want to know how the volume is changing as time is changing. dV dt. When? How fast is the volume of the balloon changing? When the diameter is 14 inches. The volume formulas are, we'll assume they're in terms of radius. So when the diameter is 14, that's another way of saying when the radius is 7. Find dV dt when the radius is 7. And what else do we have? Well, we know how much air is going in. Oh, wait. Did I write that right? Oh, yeah, okay. But that's not a good question. I didn't write that right. We're given how the volume is changing. We can't find how the volume is changing. I should read the problem when I'm writing instead of just writing on the top of my head. Okay, how fast is the radius changing is what the question says. Right here, we're given how the volume is changing. So this question's the way it's written, the way it was written, didn't make sense. How fast is the radius changing? How fast is the radius changing? So find dr dt when the radius is 7, and we know how the volume is changing, 3 cubic feet per second. So we have now turned that question into a calculus question. Now, one small thing, I really need to read these problems when I'm writing them. The units will always match up. I was just writing it quickly before this video started. The units will always match up. I'm not going to have you do unit conversions in these. So make sure I didn't write anything else wrong. So that's 2 miswritings. See, when you try to do calculus too quickly, you can do things like that. Spherical balloons being inflated. How fast is the radius changing when the diameter? Okay. Now the question is saying what it's supposed to say. There won't be any, where you have to convert from inches to feet. And if there are things like that on a test, then once I find out about it, I would take that question off the test and give you all the points. Because that would be a mistyping. So we want dr dt when the radius is 7 and the volume is changing at 3 cubic feet per second. Well, we have this volume equation, so let's differentiate with respect to time. Volume and radius are functions of time. Differentiate that with respect to time. derivative of v with respect to t is just dv dt. Derivative of the other side with respect to time, well, 4/3 and pi are constants. We have an r cubed, derivative of that is 3r squared, and then you apply the chain rule. So I'll write it like this: 4/3 pi is a constant, and then we have 3r squared. R is a function of time, so we use the chain rule. You could view this on the other side also as chain rule. You get 1 times dv dt. That's actually how I explained it in past classes, but I think that might be overcomplicating. Derivative of v with respect to t is just dv dt. And notice here there is a convenience in the numbers where the 3's cancel. So we just have 4 pi r squared dr dt. Now we just have to substitute and solve for dr dt. And I guess I'll do that over here because I shouldn't squeeze that at the bottom of the board. So we have dv dt equals 4 pi r squared dr dt. dv dt is 3. 4 is 4. Pi is pi. R squared is 7 squared, so 49. And dr dt. Solve this for dr dt, divide by that. Uh, 49 times 4 is 200 minus 4. So 3/196 pi. Units on the radius are, what was it, feet and seconds. Any questions about that one? Well, we've seen 2 related rates questions. One of them, we had to construct a triangle. In this one, we were given that it's a sphere. But both of them do describe situations which are changing as time is changing. Let's look at 2 more of these. And then I'll discuss the cylinder a little. Let's do one with a cube. Example. The volume of a cube is increasing at a rate of, let's see, 10 inches per minute. Question would be, how fast is the surface area changing? When what? When the length of an edge is 3. It's 3 inches. Cube is increasing there. How fast is the surface area? Okay. Now, this one may not seem more difficult than the last 2, but this one actually is a good deal more difficult than the last 2, and we'll see why when we do the computation. Well, I guess I'll hint at it now. We're dealing with a volume and a surface area, which gives us 2 functions. But let's first interpret this question using calculus. I'm going to interpret it under the question. I think yesterday I wrote a translate question. I wrote the solutions to the worksheet yesterday, and on those I wrote the question is asking I didn't post them, I'm posting them after class today. So here, I'll just write question is asking. What is this question asking? Well, volume is increasing at 10. How fast is the surface area changing? So we want how the surface area is changing. So find, maybe tempted to call surface area SA. I'm just going to use S. In Calc 3, do some things with surface area, and in that, it's just a capital S. Because if you have two letters around, it might look like you're multiplying things. So find ds dt when the length of an edge is 3. I'm going to call the length of an edge x because I like x the most. And what else? And the volume is increasing. And dv dt is 10 cubic inches. I could say x equals 3 inches, but again, the units are all going to match up, and unit conversions are not calculus. And on a test, I would much rather you do calculus than. So find ds dt when x equals 3 and dv dt equals 10. Well, what is a formula for S? The surface area of a cube. That's what we want. S, surface area of a cube. Well, what is a cube? A cube is one of those with an X. What is the surface area of that cube? These are all X. Well, it's the surface area of the one piece, or the one face, I guess you could say, plus the surface area of the other 5 faces. This first face has area x squared. This face up here has area x squared. And all 6 faces will have area x squared. So the surface area is 6x squared. Any questions about that? Let me erase this cube. Okay, so let's differentiate with respect to time. The surface area, if the volume is changing, then the surface area is certainly changing. And the edge length is changing. So S and X are functions of time. Differentiate. Derivative of S with respect to time is ds dt. Derivative on the other side, we have a 2x to the first. And then apply chain rule. Multiplied by the derivative of x with respect to time. Well, there's ds dt when x equals 3 and dv dt equals 10. In order to find ds dt, we need dx dt. I don't see dx dt anywhere in our rephrasing of the sentence. The example doesn't tell us exactly how the edge length is changing. It just tells us about how the volume is changing. So we're going to need to find dx dt. How can we do that? Well, this tells us something about volume, so you might suspect using the volume will help us find it, and it will. Where do I want to write it? Let's see. So for this one, I'm going to continue writing this here. It'll fit there. But to find dx dt, I'll put a star there. To find dx dt, what will we do? Well, the only other thing we have is volume. So let's consider volume. The volume of a cube with edge length x is x cubed. Maybe I'll write it over here. Volume of a cube is x cubed. Well, they're both functions of time. Differentiate with respect to time. You get a 3x squared. This is a function of time. So a dx dt will show up, and look, there's dx dt. So now we just need to solve for dx dt, substituting x equals 3, dv dt equals 10, and I wrote a little large. So 10 equals 3, x is 3, so 27 dx dt, that's sort of showing up. I guess I'll write it over here. That line down there says 10 equals 3 times 3 squared times dx dt. So dx dt, divide both sides by 27. This was feet. No, this wasn't. Just so any questions about finding dx dt? So now we just substitute dx dt and all the other things, and what do we get? We get 12 times x equals 3 times 10, 27ths. And what does that equal? 40 over 9 square inches. Is that 40 over 9? Yeah, it is, because 2 of these 3's are going to cancel. You're left with a 4 and a 9 and a 10, so 40 over 9. And it's surface area, so the units are square. Any questions about that one? Definitely, I think, more complicated than the first two. Let's do one more, in which we'll have to introduce another variable. Where do I mark it? I guess I'll write it over there. At noon, ship A is 100 miles west of ship B. Okay, ship A sails or begins to sail. Still at noon. Which direction? South. What, 25 miles per hour. And ship B begins to sail north. 35 miles per hour. And the question will be, find the rate at which the distance between them is increasing at 4 p.m. Ship A is 100 miles west of ship B. Ship A begins to sail south at 25 miles per hour and ship B north at 35 miles per hour. Find the rate at which the distance between them is increasing at 4 p.m. We have a situation which is changing as time is changing. This question is saying, what happens at a given instant during that change? So for our first one, where the ladder was leaning against the wall, it helps to draw a picture. For the second and third ones, we had shapes. So a picture was only minorly necessary if you knew the formulas, which surface area of a cube is a simple enough formula, but I still like to at least in my head think about the cube to make sure I'm counting correctly. So here, let's draw a picture. At noon, ship A is 100 miles west of ship B. So let's, here's the situation at noon. Ship A, we'll say, is over here. I'm not going to write A, maybe I will. I'm going to eventually use X and Y and eventually C. So I don't really want A and B all over the place. Well, I'll leave it here for now. So here's the situation at noon, and they are 100 apart. I'm going to put the 100 over there. We'll see why in a moment. But there's the situation at noon. But once it hits noon, ship A begins to sail south at 25. Ship B begins to sail north at 35. So just from that, we have two quantities which are now changing. We have X and we have Y. Two quantities which are now changing. And the question asks about the distance between them. Well, the distance between them is going to be measured by this diagonal quantity going through that line at 100. This distance between them is also changing, so it's another variable. Let's call it Z. And once you use X and Y, Z is pretty much the next choice. So we have here this situation. Any questions about that? Setting up the diagram. So let's turn this question into calculus, and then I'll be able to use that board over there because we won't need that. What is the question asking? Well, find the rate at which the distance between them is changing. So find what is measuring the distance between them? Z. We'll find dz dt. When? Well, it just says at 4 p.m. At 4 p.m. What happens at 4 p.m.? Well, at 4 p.m. we're going to have an X value, a Y value, and a Z value. Let's see. When so I'll write it like that. We'll have an X value, a Y value, and a Z value. What are our X, Y, and Z? Well, at 4 p.m., 4 hours have passed. Let's find X first. After 4 hours, how far has ship A traveled south? Well, it's going south at 25 miles per hour. 25 miles per hour, 4 hours gives you 100 miles. Any questions about finding X at 4 p.m.? Okay, how about Y? Well, ship B is sailing north at 35 miles per hour. 35 miles per hour for 4 hours. 35 times 2 is 70. 7 times 2 is 14. So 70 times 2 is 140. Any questions about finding Y? Now, how about Z? Well, we'll figure that out in a moment. We'll figure that out in a moment. To figure that out, we are gonna need to dissect this diagram a little more, but there will be a z value, which we will find in a moment. But what else is happening? Find dz dt when x is that, y is that, z is something. If you want, you can fill it in, it's 260, but we'll see in a moment. But what else is happening? Well, x and y are changing. X is changing at 25 miles per hour. So, and x is changing, dx dt equals 25 miles per hour. But also y is changing at 35 miles per hour. Any questions about finding, well, about translating that question? Because right now we're not going to need to reference those couple sentences in the example. So any questions about translating the question? Okay, so I'm going to have to erase this example now. So next we're going to need a relation between x, y, and z. A first instinct may be to chop up that 100 at a point in the middle and work with the two triangles. But that's not going to work because why? It's not going to work because where this gets chopped up in the middle is changing, which would cause us to have a fourth variable come into play. And 3 variables is more than enough. But what else can we do? Well, I have other colored chalk. We can use that. What else can we do? Well, we can make a big triangle like this. So now we have this tall triangle. And because this bottom piece is a rectangle, we know the lengths of of its sides. Any questions about what we added to this diagram to help us find an equation? What is our equation? Well, we'll use the Pythagorean theorem on this triangle here. Bottom squared is 100 squared, 10,000, you leave it as 100 squared. I'll leave it as 100 squared, I guess. Plus the other side, the tall side is x and y, so x plus y. Equals hypotenuse squared. So z squared. Any questions about finding that equation? Okay. Let's see, should we solve it first or find z first? Let's differentiate and then we'll find z. So any questions about finding that equation? We'll see why writing it as 100 squared doesn't really make a difference. Okay, so let's differentiate with respect to time. Derivative of 100 squared with respect to time is 0 because it's a constant. How about the derivative here? Well, it's a function squared. Derivative of something squared is 2 of them to the first power. But then you apply chain rule. X and y are functions of time. So the derivative of x plus y is 1 dx dt plus 1 dy dt. So right here, this large parenthetical showed up because of the chain rule. On the other side, we have z squared. Derivative of that is 2z to the first times, by chain rule again, x, y, and z are functions of time, so time is dz dt. And now we need to substitute and solve, but in order to substitute, we need z. So before substituting, let's find Z. And to find Z, we're going to use this large triangle. You could jump to that equation over there. Triangle. This top side or tall side is x plus y. X plus y is 240. So here we have a 100, 240 as our legs. What is Z? Well, this is a scaling of a 5, 12, 13 right triangle. 5 times 20 and 12 times 20. So Z is 13 times 20, which is 260. So 3, 4, 5 triangles show up sometimes. 5, 12, 13 triangles show up sometimes. There are others, but you know, I usually stick to 3, 4, 5, and maybe a 5, 12, 13. Any questions about finding Z? So now we just need to substitute and solve. Notice here there is a 2 on each piece. Maybe I'll write that. 2x plus y, 100 plus 140 times dx dt plus dy dt, 25 plus 35 equals 2z, which is 260, times dz dt, which is what we want to solve for. And what do we get? Well, first the 2's cancel, so I'm just going to ignore those. We have 240 times 60 equals 260 z dt, where we can't, well, divide both sides by 2. Could also divide by 10. I'll leave it like this. Divide by 260, and what do we get? Divide by 260. 240 divided by 260 is 12/13 because 20's cancel. 12 times 6, 72. Times 6, 72, and the 13 doesn't cancel. And what are our units? Probably miles per hour. Yes, miles per hour. Any questions about that one? So this one, now we covered 4 examples. The last 2, I think, are significantly harder than the first 2 because of the additional variables. But drawing a picture and translating the question is really, I would consider that the bulk of the work. Because once you get there, you can generally construct an equation and then differentiate and substitute. Any questions about that? So we covered what did we cover? We covered one with a sphere, we covered one with a cube. You could also have one with a cylinder. On the worksheet, there is one with the surface area of the cylinder, I believe. And I posted a document called cylinder, which discusses how you can think of the volume and surface area of a cylinder. It's 2 pages. On the first page, it discusses the volume of a cylinder. A cylinder, well, a box is a rectangle extended in the 3rd dimension. And the volume of a box is the area of the one side times the length you're extending. So it gives you, the one side times the other side times the other side. A cylinder is the same basic thing, except instead you're taking a circle and extending. So the volume of a cylinder is the area of that circle times how much you're extending. Area of the circle, pi r squared. The other is generally considered the height of the cylinder, so pi r squared h. And that's the first page of that document. The second page discusses a surface area. Now the volume formula, that can be memorized, and that's not that rough if you just had to memorize it. The surface area, I think, is much harder to memorize because there are 2's and pi's and r's all over the place. But a cylinder, a closed cylinder, meaning top and bottom are closed, consists of a circle on top, a circle on the bottom, and then its outside shell. And if you want the surface area, you're going to need the area of that top, the area of that bottom, and the area of the outside shell. Area of the top and bottom are both pi r squared because they're circles with radius r. But what about the outer shell of the cylinder? Well, conveniently, if you slice that down the middle and not fold it out, it's not folded, and unroll it, it becomes a rectangle, where the one side of the rectangle is the height of the cylinder, and the other side of the rectangle, this top in my paper diagram, is the circumference of that top circle. Circumference of a circle is 2 pi times the radius. The other length is the height. So you have 2 pi times the radius times the height for the outer shell, and then plus the 2 circles, so plus 2 pi r squared. So, you could memorize those formulas. I do find them hard to memorize. I find it much easier to have circles in mind and use those to figure out the volume and surface area of the cylinder. And on the worksheet, there was one, I guess I have the worksheet right in front of me. It was, oh no, it was volume I asked about in problem 4 on the worksheet. Big product rule is going to show up there. So now I could ask something on a cylinder. There's one other type of related rates question. So this week is week 4. Next week is week 5. Next week, we're going to cover a topic called optimization. And related rates and optimization, there's a technique that could show up in both of them. And in the optimization one, I covered the technique in detail. For the related rates, I just posted it as a document now. There's a document posted called something like related rates example or additional related rates example. And in it, it has an example. A water tank has the shape of an inverted circular cone and so on. Water is being pumped into the tank. How is the water level rising? Now, in this one, you do need to know the volume of a cone. But since I'm not covering it in detail here, I won't expect you to memorize that. Meaning, if I do ask a cone question with the volume on a test or the final, I'll just write down the volume of a cone is given by, and I'll give you the formula. But in this example, a similar triangle argument shows up. A similar triangle argument could also show up in next week's topic. And in the video, it's one of the video lectures. In that, I do cover the similar triangle argument in detail. And I also mentioned, I made the video 2 days ago. I probably mentioned this could show up in related rates. Yeah, I think it's the last sentence of the video. And if you want to see what it looks like for related rates, there is a document posted with an example. So on this test, on the final, if there is a similar triangle, it would be optimization rather than this, since I covered the optimization in detail. But if you do want to see what that would look like, it is here. Meaning, for exam 2, you don't have to worry about similar triangles. Well, you also don't have to worry about cones. I already decided which related rate example is going to be. Any questions about that? Now, the water being pumped into a tank. So we discussed, ladders sliding down a wall, boats sailing away from each other, making a triangle. Now, another family of standard related rates examples is something like a tank with a certain shape is being filled, and it asks what's happening at it with certainty. But for related rates questions for this test, the 4 we covered. What's being asked on the worksheet? 3B probably, well, definitely won't be asked, something like that. But triangles, cubes, maybe a cylinder, not a cone. Any questions? Hope I didn't introduce additional confusion. I feel like that was more clear in my head. That's when I turned it into words. So let's cover now another result called L'Hopital's rule. And let's do it on that board over there. So on worksheets and tests and homeworks, probably not worksheets, the directions for limits from week 2 frequently said, evaluate the limit. You may not use L'Hopital's rule, whatever that is. Now, the reason that is because we didn't have it, but the other reason that it is because it uses the derivative and it relates some limits to some derivatives, and we didn't have the derivative. So right here, we will discuss this rule. In a calculus class, there's usually a blend of people who have seen calculus and people who have not. And those who have seen it tend to like to use this rule for limit computation, because for some of them, it makes it a little easier. But let's cover it now. We're going to look at actually 3 different forms this can take. But let's state it first. So L'Hopital's rule relates nicely some limits to their derivatives. Well, maybe not their derivatives, to some derivatives. So if direct substitution for this limit as x approaches a, or f of x over g of x gives 0 over 0, or, so I'll be a little informal in the statement and more formal in the examples. A could be infinity. This limit could be as x goes to infinity. And you can think of substitution with that. But if a direct substitution argument gives a 0 over 0 or an infinity over infinity, where they can be positive or negative in each case, then what? Let's erase this board. Then what? the limit as x approaches a, or a could equal infinity. And I don't want to write the same thing twice with infinity because this is fine. Then the limit in question equals this limit. So if a direct substitution argument gives you a 0 over 0 or an infinity over infinity with either sign on the infinities, then the limit in question equals this new limit, the limit of the derivative of the top divided by the derivative of the bottom. So notice here, we're not saying take the derivative of the whole thing, meaning there's no quotient rule. Here, L'Hopital's rule does say that all we need to do is take the derivative of the top and divide by the derivative of the bottom. Any questions about the statement? Statement may be a little confusing, so let's look at a few examples. This will be the first form one of these limits can take. Let's see, x squared. So let's do this limit. We're going to do 3 of this first form. Maybe those are considered. Let's just do something. Limit x approaches 4 of x squared minus 3x minus 4 all over x squared minus 2x minus 8. Now, our first observation here is that we could, well, our first observation is, does substitution work? Still, if you do this substitution and get an actual number, then you're done. None of these examples today will that argument apply to. But what happens when you substitute? You get 16 minus 12 minus 4, 0, over 16 minus 8 minus 8, 0. So you get a 0 over 0. L'Hopital's rule says we can compute this limit by using this formula. So when we use L'Hopital's rule, I always like to mark the equal sign, and I request that you mark the equal signs as well when you use L'Hopital's rule, just to make it absolutely clear what's going on to the grader, which is fine. So here, because we get a 0 over 0, you could also mark, it's a 0 over 0, so we're using L'Hopital's rule. We're going to use this formula. L'Hopital's rule says that limit equals this limit, the same limit of the derivative of the top, which is 2x minus 3, divided by the derivative of the bottom, 2x minus 2. So again, no quotient rule. L'Hopital's rule doesn't say take the derivative of the whole fraction. It just says derivative of the top over derivative of the bottom. And does substitution work now? Well, substitution gives 8 minus 3 divided by 8 minus 2, which is a number. Which number is it? It's 5 divided by 6. So this limit is 5/6. Now, technically, for this one, we didn't need L'Hopital's rule, because the top and the bottom did factor. But now that we have it, we could do this same limit another way. And that would factor as what? X minus 4, x plus 1 over x minus 4, x plus 2, x plus 1 over x plus 2. Any questions about that first limit? Let's do some more. Now, this limit is an important limit, the next one. So let's do this limit. Just like that first limit, there are two different ways of doing this limit. There is a way to do this limit using L'Hopital's rule. There's also a way of doing this limit using the squeeze theorem. The argument for this with the squeeze theorem is a little more complicated than the argument we did for just sine of x with squeeze theorem, where we constructed a triangle in the unit circle in order to set up our squeeze theorem equation. And maybe I'll post the details for the squeeze theorem argument with this. I'm not going to ask that because it's a, well, tougher argument than it's tough enough that I don't think it should be tested. But there is a way of doing this limit using squeeze theorem, but we can also use L'Hopital's rule. This limit is actually very important in calculus. It's used to prove the derivative of sine formula using the f of x plus h minus f of x over h as h goes to 0. But what can we get here with a direct substitution? Well, you get sine of 0, which is the y value, which is 0, divided by 0. So it gives you a 0 over 0. And when that happens, you can use L'Hopital's rule. And what does this equal? Well, it's the same limit, but it's a different function inside the limit. Derivative of sine of x is cosine of x. Derivative of x is 1. And now what is this limit? Well, as x goes to 0, cosine x goes to cosine 0, which is the x value. 1 doesn't change. So this limit here is 1. Any questions about that? Let's do one more like this, and then we'll do two that are related. E of the x minus 1 over x squared. Limit as x. I really should be labeling these like A, B, C. X goes to 0, e to the x minus 1 over x squared. And this one would be part A. Okay. So what do we get here upon direct substitution? Well, e to the 0 minus 0 minus 1. E to the 0, remember, is 1. Any non-zero to the 0 is 1. So we have 1 minus 0 minus 1. 1 minus 1 is 0 over 0 squared. So we do get a 0 over 0. And when we get a 0 over 0, we can apply L'Hopital's rule. Whenever we get a 0 over 0, we can apply L'Hopital's rule. Derivative of the top, derivative of e to the x is itself, derivative of negative x, negative 1, 1 is constant, negative 1 is constant, derivative is 0, divided by 2x. And now, what happens when we substitute here? Well, let's see what happens when we substitute here. We get e to the 0 minus 1 over 2 times 0. E to the 0 is again 1. 1 minus 1 is 0. So in this next limit, we got another 0 over 0. But we can apply L'Hopital's rule a second time. This is still a limit whose form upon substitution is 0 over 0. So we can apply L'Hopital's rule. is 0 over 0. It's still the limit as x approaches 0. Derivative of the top is now just e to the x. Derivative of the bottom is just 2. And now as x approaches 0, you get e to the 0, which is 1 divided by 2, a number. So that is the limit. Any questions about that one? So L'Hopital's rule, you may have to apply it twice in the same one. There are some examples where you could kind of get trapped in a L'Hopital's rule loop. And some of them with trig that happens too. But it is in many ways a convenient rule. Let's do how about these two limits? Let's do them over here because so L'Hopital's rule also applies when you're taking a limit as x goes to infinity. We'll call this one a new example, actually. Example, do these two limits a. Limit x to infinity or negative infinity. L'Hopital's rule applies as well, if the substitution gives 0 over 0 or infinity over infinity. More on what we mean by substitution as x goes to infinity. Let's do these two limits. Now, first of all, we could do these two limits by our techniques from week 2. Divide by x squared, divide by x squared, or flip it as x goes to positive infinity in that case. We could also, in this case, since it doesn't say not to use a theorem, and on this test, if a question like this shows up, you may use the week 2 theorem. On the final, it won't say that you can't, so you can't. That was just an exam 1 thing, because there is some nice calculus to be seen from dividing everything by x squared. But that's a week 2 topic. But what else can we do to compute these limits? Well, we can see if L'Hopital's rule applies. Now, what do we mean substitute infinity? Because infinity is not a number. You can't substitute infinity. But we have here a polynomial divided by a polynomial. Let's just work with this one for now. We have polynomial divided by polynomial. As x gets large, as x goes to infinity, a polynomial is going to be dominated by its largest degreed term. So the top here is going to be dominated by this 2x squared term as x gets large. 2x squared gets large much faster than 5x because of that exponent. What does that mean for us? Well, it means for us, if we want to consider this fraction's behavior as x goes to infinity or negative infinity, then all we really need to look at is what the largest term does as x goes to infinity. As x goes to infinity, just looking at the top, x squared goes to infinity times 2, that goes also to positive infinity. On the bottom, x squared again goes to infinity, but there's a -5 on it. That's going to cause it to flip over to negative infinity. So here, as x goes to infinity, the form this first limit takes is infinity over negative infinity. L'Hopital's rule applies when our fraction takes the form of any infinity divided by any infinity, meaning positive or negative divided by positive or negative. And we can apply L'Hopital's. So again, the statement of L'Hopital's rule that we covered, that a value could be a limit as x goes to infinity. That's derivative of the top is 4x plus 5. Derivative of the bottom, negative 10x plus 0. Any questions about that first argument? Now, how about here? Well, again, we have, it's a line over a line, but still it's polynomial over polynomial. What happens as x goes to infinity? Well, each polynomial is dominated by its largest term. In this case, the largest terms both have degree 1, x to the first power. As x gets large, 4x goes to infinity. As x gets large, negative 10x goes to negative infinity. So again, we have an infinity over an infinity. We can apply L'Hopital's rule again. Derivative of the top is 4, derivative of the bottom is negative 10. This is a constant, and as x goes to infinity, a constant doesn't change. So we get negative 2/5 is that limit. And notice that is consistent with the coefficient argument, which you may use if one of these shows up on the test. Any questions about that limit? Okay, now how about part B? Well, the same argument applies, but we're considering as x goes to negative infinity. As x goes to negative infinity, the polynomial is still going to be dominated by its largest exponented term. Degree of the top is 2, degree of the bottom is 2. As x goes to negative infinity, x squared goes to positive infinity. 2 times x squared also goes to positive infinity. As x goes to negative infinity, x squared goes to infinity, times the negative 5 flips that over to negative infinity. We have an infinity over an infinity, meaning a positive or negative over a positive or negative. So we can apply L'Hopital's rule. You could also, if you want, flip this over, make it positive infinity and go up here, but for L'Hopital's rule, that doesn't really save any work. What limit does it equal? Well, the derivative of the top, 4x plus 5, derivative of the bottom, negative 10x. And it looks like we're back up here, and we sort of are, but we will see in this step a difference, a slight difference. What happens as x goes to negative infinity? Well, again, polynomial is dominated by its largest term, 4x, negative 10x. As x goes to negative infinity, 4x goes to negative infinity. Because that positive 4 is not going to flip that over the x-axis. But this negative 10x will go to positive infinity because the negatives would cancel. We get a negative infinity over infinity. We can apply L'Hopital's rule one more time. Limit as x goes to negative infinity of 4 divided by negative 10, which, just as before, is negative 2/5. So for these limits, we now have 3 different ways they could be done. And starting on exam 2, you can use whichever way you want. Any questions about this one? Okay. So we took the limit as x goes to positive infinity and the limit as x goes to negative infinity of this function. So I'm just going to observe right at the end of it. Notice we may conclude that, is that proper grammar? I don't think it is, maybe it is. I've never been good with facts and grammar. But let's just say, notice, we took the limit as x goes to positive infinity and the limit as x goes to negative infinity. So we may conclude that this function has horizontal asymptotes. Well, only one in this case. Y equals negative 2/5 from the previous two computations. Now, so, and that example didn't say find the horizontal asymptotes, it just said compute these limits. But, we did the two limits, which would give the horizontal asymptotes, and they happen to be the same, so horizontal asymptote. Any questions about that? On this test, I guess I'll give it away now. I'm not asking a horizontal asymptote question on this test. But I may ask one on the final. Probably will ask one on the final. Any questions about that? Okay, so those first 5 limits we took represent the first general form L'Hopital's rule can take. A limit which is a fraction which looks just like the statement, meaning we got 0 over 0 or an infinity over infinity. Let's look now at another couple limits on which we can apply L'Hopital's rule. How do I want to start this? Limit as x went to 0 from the right, 1 over x was infinity, and limit x goes to infinity, 1 over x is 0. So these two limits we saw a few times, and in both cases, for each case, we looked at the graph of 1 over x and interpreted that. As x went to 0 from the right, this curve went up to positive infinity. And as x went to infinity, this curve went to 0. Now, we can't divide by 0. We can't divide by infinity. But we can use these observations to help us see how terms whose limits as x goes to 0 or as x goes to infinity take these form. We can use, that was a lousy sentence. We can use behaviors of these limits to understand other limits which take these forms. We can use these observations algebraically. So I'm going to say from this, we observe in their respective limits so it is important that we are in the back of our mind seeing limits, but in our consolidated observation that we're about to make, we aren't necessarily looking at limits. We can think of, that's not an equal sign, that's like a jagged equal sign. There's no real symbol for this. So I'll put a really squiggly equal sign. 1 over 0, as the denominator goes to 0 from the positive side, behaves like an infinity, and 1 divided by something which goes to infinity, really jagged equal sign, behaves in their limit, meaning as the denominator approaches these terms, the limit will go to infinity, the limit will go to 0, assuming the signs work out nicely. I'm going to throw this in quotes just to further emphasize these are not actual equal signs. But we can use behavior, assuming they are equal, to understand the next thing that we're going to do. Well, any questions about this very informal statement here? We'll see why we're using this in a moment. What we're really doing here is manipulating limits and turning them into algebraic symbols. And we can use that type of symbol manipulation to see what we're going to do for our next limits. So maybe I'll write that. We can use this kind of symbol manipulation to turn limits into, turn some limits into limits on which L'Hopital's rule applies. I'll put a colon here to demonstrate what this sentence is actually saying. So those squiggly equal signs in quotes over there represent a form of symbol manipulation where in the back of our minds we're realizing those make sense only as limits. Now I know it's tempting in a calculus class, I did the same thing, to just say dividing by infinity gives a 0, dividing by 0 gives an infinity. But that is true only in the limits. So we can use that observation to turn some limits into other limits, well, into the same limits, on which L'Hopital's rule applies. So what would that look like? Well, one example, what if we had a limit whose form took 0 times infinity? So there we have a 0 times infinity. And let's write that over a little so I don't go on to the next board. Meaning, with a substitution argument, we get a 0 times infinity. Well, L'Hopital's rule doesn't apply to limits which look like that. L'Hopital's rule applies to infinity over infinity, or 0 over 0. But what we can do is use either the first or the second observation over there and put one of these in a denominator. I'm going to put, which one do I want to put in the denominator? Let's use the second one. The 0 behaves in the limit like 1 over infinity, meaning let's turn the 0, let's put the 0 term in the denominator by observing in the limit that 0 behaves like a 1 over infinity. So if we put that 0 in the denominator, we now have 1 over infinity times an infinity, which then when written as one fraction, is a form on which L'Hopital's rule applies. Let's do an example. Let's find a large piece of example. Limit x goes to 0 from the right of x times the natural log of x. Now, in that, infinities for L'Hopital's rule say the sign of the infinity doesn't matter. So if they're negatives, that's fine. But what does this limit do upon a direct substitution? Well, you would get a 0 times, as x goes to 0 from the right, what does log x do? Well, it's a negative infinity. Why? Well, graph of log x looks like that. As x goes to 0 from the right, this goes down to negative infinity. Meaning, using a substitution-like observation, this takes the form 0 times an infinity. Any questions about that first observation here? Now, L'Hopital's rule doesn't apply to a limit which takes this form. It doesn't directly apply to a limit which takes that form. We need to write it as a quotient so that it's a 0 over 0 or an infinity over infinity. Now, that can be done by putting the infinity in the denominator. With these, it is strongly recommended that you leave the logarithm term where it is. Meaning, if we're going to turn this into a fraction, let's do it working with that x term. Maybe I'll write this one on the next line. Log x, we're going to leave up here, but we're going to put the x in the denominator. How can we do that? An x in the numerator is the same as a 1 over x in the denominator. Now, why is that? Well, I think it's easier to see going from this step backwards. You know, divide by 1 over x, same as multiplying by the reciprocal of 1 over x, which would put an x next to the logarithm of x. But what we're doing is putting this x in the denominator so that the limit is now in a form on which L'Hopital's rule directly applies. Any questions about putting that 1 over x, or well, putting the x in the denominator? That's and I think that's probably the most confusing step in L'Hopital's rule. Putting something in the numerator into the denominator, which causes us to take its reciprocal. So now, why does L'Hopital's rule apply to this one? Notice I didn't put an h here. We're not using L'Hopital's rule for that first equal sign. We're just using algebra with this type of symbol manipulation in mind. I kind of bypassed that middle line. But what do we get upon a direct substitution argument? Well, log x, using the graph that I erased, goes to negative infinity. What about 1 over x? 1 over x goes to infinity as x goes to 0 from the right. You can look at that curve or what I erased up here. Week 2, I think we started discussing that. But this takes an infinity over infinity form. You can apply L'Hopital's rule now. Derivative of log x, 1 over x, derivative of 1 over x. Well, using a power rule argument, get negative x to the negative 2, which is the same as negative 1 over x squared. Of course, you could leave it as the negative exponent, but we are going to have to simplify this fraction a little. Now, what can we do with that fraction? Well, we can see if any x's cancel. We still have not taken a limit, but 1 over x divided by negative 1 over x squared, or multiplied by the reciprocal. Reciprocal of 1 over x squared is x squared. So you have 1 over x times x squared with a negative. So you're just left with a negative x. So 1 over x times x squared over 1. One of the x's cancels, and the negative stays there. As x goes to 0, negative x goes to 0. Any questions about that one? So right here, we saw that something which doesn't immediately look like L'Hopital's rule applies to it can actually have L'Hopital's rule apply to it. Meaning up here, we have this product, a0 times n infinity, and we turned it into a quotient on which L'Hopital's rule applies. There are three other types of limits that can apply to. So let's write that over there. So again, this will be symbol manipulation to demonstrate the algebra we're going to have to eventually do. Well, let's do it like this. I'm going to fill this board with something, but the goal will be to do this limit. So we had derivatives. We had a power rule. We had an exponential rule. Yesterday we discussed this. But we didn't have a derivative of x to the x. Similarly, we don't have a limit of x to the x. But what can we do? Well, if we had a substitution, we could, but here, substitution gives 0 to the 0, which isn't a number. But what we can do is put a logarithm on that, turn it into a product, which can turn into a quotient on which L'Hopital's rule applies. So let's write that here. Let's say it like this. Given a limit, not limits. Given a limit which takes the form, three forms. 1 to the infinity. Infinity to the 0. 0 to the 0. These three forms are called indeterminate forms because in the limit, these can actually, each one can actually behave like any number. This first example, we'll see it looks like 1. And, well, we'll see more. But if you try to take a limit and it takes one of these forms, meaning using a substitution-like argument, if it takes one of these forms. For example, this limit that we're going to do after that discussion takes that last form because the substitution gives us 0 to the 0. But given a limit which takes one of those forms, we can introduce a logarithm and turn it into a form on which L'Hopital's rule applies. So I'll say instead of and, so that L'Hopital's rule, remember, L'Hopital's rule works only on fractions. These aren't fractions, they're some sort of exponential. But a logarithm can turn that into a product, and a product can be turned into a quotient. So that L'Hopital's rule eventually, I'll put that in parentheses, applies. And what would that look like? Well, let's demonstrate that with the first one, I guess. Logarithm, again, symbol manipulation here to show the algebra we're doing. Logarithm of this form looks or behaves like, bring the exponent out front, infinity times a logarithm of 1. Logarithm of 1, remember, is 0. So that behaves like an infinity times a 0, which we can then apply an argument similar to the previous example by, well, maybe I'll write it like that. In the previous example, we observed that a 0 in its limit can behave like an infinity, or well, 1 over infinity. And we then have a fraction on which L'Hopital's rule applies. So given one of these, throw a logarithm on it, move the terms around using logarithm properties, turn this product into a quotient. L'Hopital's rule now applies over here. And a similar argument will work for the other two. I won't write that in because it's basically the same. The second one would be 0 times log infinity, which you can then do one of these two again. 0 to the 0 would be 0 negative infinity, and you can do one of these again. But let's see what this looks like with an actual example. Let's use this example. But the first thing we notice here is that introducing a logarithm creates a new function. So to find the limit we want to find, we're actually going to find a separate limit, and then we're going to use that to find what we want to find. So let's look at what that looks like here. This limit takes a 0 to the 0 form. So what does this equal? Well, because we're going to use another limit, I like marking right at the beginning that we're going to do a good deal of side work, and then undo that side work for that last step. So as side work, what are we going to compute? Well, we're going to throw a logarithm on. Throw a logarithm on this 0 to the 0. Throw a logarithm on it. Logarithm of now x to the x. What does this equal? Well, use logarithm properties. Bring that x out front. You get x times the logarithm of x. And now, what do we have? Well, we have actually the exact limit we had in the previous example. So with this one, what would we do? we proceed as in the previous example by putting this x in the denominator. Equals, so I'm not going to write the same thing as the previous example, so I'll just say by previous example, this one equaled 1. If you didn't have that previous example, well, we would have gone through that argument. But the previous example told us that that limit is in fact 1. Now, another thing to observe about this one is that this limit we computed isn't the limit we wanted. It differs by a logarithm. To get the limit we want, we would have to get rid of the logarithm. How can we get rid of a logarithm? Well, we can do that by taking exponentials of everything. Exponential is a continuous function, so the limit will travel across it. Meaning, if we want the limit we want, we would take the exponential of this. Oh no, that limit was 0, wasn't it? Was I looking at the wrong one? Oh, sorry, that limit was 0 in the previous example. Sorry about that. Previous example, x log x was 0. Yeah, the one under that I wrote 1. X cotangent x. Sorry, previous example was 0. So here, if we want the limit we want, we would need to get rid of this logarithm, which we can do by taking the exponential here, taking the exponential here, taking the exponential here. So this limit is e to the 0, which equals 1. When I wrote 1 here, I actually was not thinking of that. I just looked at 2 lines lower in my notes. So this limit we wanted is e to this number. So to compute the limit we want, we threw a logarithm on our function and went from there. Any questions about that one? Let's do one more of these, and then we'll cover our next topic, which, you know, we're just going to introduce the topic a little. Example. Compute this limit as x goes to 1 from the right. Notice in the last 2 limits, we had 0 from the right. Now the reason for that is because of the logarithm not being defined for 0 or negative numbers. And here, because of the shift, that's going to move over to 1. Compute this limit. X goes to 1 of x to the 1 over 1 minus x. Okay. Try a substitution. You get a 1 to the 1 over 1 minus 1, which behaves like 1 to the 1 over 0, which behaves like 1 to the infinity. In this case, technically, that becomes negative because we're on the right of 1. But either way, this one is a 1 to an infinity form. And to compute a limit like that, we can throw a logarithm on and apply L'Hopital's rule. So again, what I like to do, just to remind myself we're doing side work, is write that we're doing side work by saying it equals by side work. What does it equal? Well, let's see. We're doing this limit now, a logarithm of that quantity. Logarithm of that quantity, bring the exponent out front, gives you 1 over 1 minus x times the natural logarithm of x. Now to apply L'Hopital's rule, well, any questions about the exponent coming out front here? Large exponent in this case. So next, we're going to write this as a quotient so that L'Hopital's rule will apply. This right here isn't written as a quotient, it's technically a product. But we can put this first term in the denominator, which conveniently just looks like we're multiplying them in this case. And now L'Hopital's rule will apply because substitution here would give a 0 over 0. So we've been having infinities over infinities. Just by flipping everything around, that can eventually be 0 over 0 as well, using those algebraic symbol manipulation observations. This equals now the limit of the derivative of the top, 1 over x, divided by derivative of the bottom, -1. And as x goes to 1, let's do, well, it goes to -1 over 1. And I'm just right here, just reducing that fraction so it looks nicer. As x goes to 1, this goes to -1. So that limit went to -1. But again, this is not the limit in question. The limit in question doesn't have a logarithm on it. So to find the limit we want, we would need to get rid of the logarithm, which can be done by taking exponentials in all steps, which makes our answer e to the -1, because that was a -1. And of course, you can write that 1 over e if you want. That's fine. E to the -1 is also fine. And for this one, actually, e to the -1 might be nicer because it shows how you're using that limit. Any questions about that? Okay, so we covered a bunch of L'Hopital's rule examples. I think these last few examples take a good amount of practice just to get used to the forms they take. So, two things. First, I posted these L'Hopital's rule arguments, ones we've covered today, have kind of worked out nicely, but that doesn't always apply. They can get really unpleasant really quickly. So I did post a document, well, a 1 page with a couple more examples like this, just so you could see how inconvenient some of the calculus and algebra gets. Now, if one shows up on the test, it would work out, more nicely than these that are posted. But there are a couple more if you want to look at them. That's if you want. But also, these examples do take a good amount of practice, and because of that, they will not show up on exam 2. But the first few examples we covered with L'Hopital's rule may. So the first example, which had the 3 different limits, the one as x goes to 4, the sine x over x, the e to the x minus 1 over x squared. And then the limit as x went to infinity, x goes to -infinity of 2x squared plus 5x over -5x squared minus 1 or something. Those first 5 L'Hopital's rule limits could show up on exam 2, but all limits after that will not show up on exam 2. And again, remember, not showing up on exam 2 is means almost definitely that it will show up on the final. So I'll just write that as a remark. All L'Hopital's rule examples after the horizontal asymptote observation. So after does not mean after and including, it just means after that observation, meaning once we started doing the 0 times infinities, and then these with logarithms. But all the examples after that will not be on exam 2, and you can reasonably expect from that that they will be the final. Meaning, problem, so worksheet 4, problem 5 could show up. So I'll write that, worksheet 4, problem 5 could show up, meaning something like, I don't think I ever asked the same question. But problem 6, those 3 parts won't show up on exam 2. And I capitalize E because I capitalize it up there. So when you're practicing L'Hopital's rule problem, you can restrict yourself to something like problem 5 on worksheet 4. But one like worksheet 4, problem 6 will show up on the final. Almost definitely, closer to definitely than almost definitely. Any questions about that? I think those take more than 3 days to sink in, even if you work on them each day. So definitely a better final exam question. Okay. Let's move on to our last topic, which could show up. Antiderivatives. Now, we have derivative rules. We have 16 derivative rules and then the chain rule. That entire process can be reversed. And reversing that process, and reversing that process produces some rules. But going in reverse, we will see a little bit today and a little bit more next week. We will see that reversing that process isn't as easy. Meaning, with a derivative, we started with the function, we found a derivative. Reversing that process, we're going to start with the derivative and go back to a function, an original function. Why is that not as nice? Well, for example, there's no product rule. So if you start with a product, you can't really go backwards. But let's define this definition. And antiderivative of f of x, lowercase f of x, is a function whose derivative is lowercase f of x. So we're going to use here capital and lowercase f. Right now it just says lowercase. But we will also use a capital F, but I don't, using the capital F and the lowercase f in a similar context is standard in calculus for many years. And something that's standard for many years, even if it may look confusing, generally is standard because it's less confusing than an alternative. And I side with the side which says having a capital and a lowercase f is as clear as we can make it. Now again, no capital F yet, but in this example we will use it. Before discussing antiderivative rules, let's see if we can find one. Find an antiderivative derivative of this function. And here we're going to call our antiderivative capital F. Now, another reason antiderivatives are a little more complicated than just finding derivatives is that the derivative was unique. Given a function, it had a unique derivative. Antiderivatives are not unique, meaning given a function, you can find multiple, in fact, infinitely many antiderivatives. Find a function whose derivative is 5x to the fourth is another way of phrasing this. Find a function whose derivative is 5x to the fourth. Well, have we seen a way to get to 5x to the fourth by taking a derivative? Well, we have. The derivative of x to the fifth is 5x to the fourth. So right here, capital F of x equals x to the fifth is an antiderivative of 5x to the fourth. And whenever I find antiderivatives, I like to check my work by taking a derivative. Derivative of x to the fifth is 5x to the fourth. So this right here is one answer. There are many answers. You could have also said, you could have taken capital F of x equals x to the fifth plus 7. The derivative of that is 5x to the fourth. And you can see that that 7 could have been any constant because the derivative of any constant is 0. For today and for our exams, or not for our exam 2, you don't have to worry too much about finding more than one, meaning you don't have to worry about that. We're going to formalize this constant a little more next week. For this exam, I'm more concerned with your working with the couple of rules that we're going to work on next. What are those rules? Well, let's look at this a little more closely. What we really did here was, in a sense, reverse the power rule. How? Well, let's write that over here. Let's call it a chart of antiderivative rules. And the chart, so we had a derivative chart, which was function and derivative. I'm going to do the same thing, but with antiderivatives. So function, antiderivative. Now, with the derivatives, we had 22 rules. With this, we're actually going to have, I believe, 9, 6 of which are the trig ones. Is that correct? Oh no, 10 exponential. Let's do, what did I put on the worksheet? What did I put on the homework? Okay, let's do 9. The other one we'll cover next week. 9 rules. First, we have a constant rule. The derivative of constant times x is that constant. So antiderivative of the constant, which we're going to call k here, is k times x. Next, we have a power rule. X to the n. X to the n. The power rule for the derivative said multiply and subtract. The antiderivative rule is going to flip that around. Instead of multiply then subtract, we're going to add and divide. Add 1 to the exponent and divide. Next, the derivative of e to the x is itself. So an antiderivative of e to the x is e to the x. So this is going to be a chart with 9 antiderivative rules. The next 6 are just going to reverse the trig rules, the trig derivative rules. But we can see that given a function like this, we can apply rule 2. Now, what would that look like? The power rule for antiderivatives. Well, we could say by power rule for antiderivatives, anti-DER test. For by power rule, what would we get? Well, we would get that our capital F, our antiderivative, is 5 times what? 1 over 4 plus 1, x to the 4 plus 1, which is 5 over 5, x to the 5, 1, x to the 5th, which does give us our x to the 5th. So some of these, once you do more practice with these, for something like this, you may be able to jump there. But in general, I would recommend using the power rule. Now, the other 6 rules just reverse the trig rules, so I'll write them here. Which one do I want to write first? Antiderivative of cosine x. Sine x, again, because the derivative of sine is cosine. Antiderivative of sine x. Negative cosine x, because the derivative of cosine is sine, or is negative sine. Another reason the antiderivative rules aren't as convenient is illustrated by the trig rule, the trig functions. The antiderivative of tangent is actually complicated to find, but the antiderivative of secant squared is not, because we have the rule for tangent. Next, the derivative of cosecant is negative cosecant cotangent, so an antiderivative of cosecant cotangent is negative cosecant. The derivative of secant is secant, derivative of secant x is secant x tangent x. So antiderivative of secant x tangent x is secant x. And last, the derivative of cotangent is negative cosecant squared. So antiderivative of cosecant squared is negative cotangent. We have these 9 rules on this test. I will list out those 9 rules, but you will have to show how they're used. Now, I'll give you that list since it's just a couple days from now. On the final, I won't give you a list because that's a couple weeks from now. But let's just look at an example. Now, just like with derivatives, you can do these piece by piece, meaning you have a bunch of antiderivatives, there are a bunch of functions added together. You can go through one by one. Let's just do this one example. Find an antiderivative of lowercase f equals, let's put 4 or 5 pieces and let's illustrate a few rules. x to the 7th plus 4x cubed plus, let's do minus x plus 1 minus e to the x plus sine x. Well, we can do these piece by piece using our 9 rules. The first 3, actually the first 5 use rules 1 through 3. First one uses our power rule. Add 1 to the exponent, you get 8, and divide. Divide makes it 1/8, and x to the 8th. For the next piece, we do the same thing. Add 1 to the exponent and divide. 3 plus 1 is 4, x to the 4th, and the 4's cancel. For the next one, we have an exponent of 1. 1 plus 1 is 2, so negative half x squared. Next one, we have a constant. Our first rule told us how to handle constants. Constant times x. Next, we have negative e to the x. The derivative of e to the x is itself, so the derivative of negative e to the x is, or so the antiderivative of negative e to the x is itself as well. And last, sine x. We had a given sine, the antiderivative is negative cosine. So here, antiderivative of sine is negative cosine. If this said minus sine of x, we'd have plus cosine x. But here, we're just using those 9 rules. Any questions on that? So again, that list of 9 rules, that chart, will be attached to the test. But you know, you can work on the couple on the worksheet. They're similar to these. Any questions? Okay, well, the homework for this week, I would recommend handing in sooner rather than later so that you can start preparing for the test sooner rather than later.